When evaluating the bottlenecks slowing down artificial intelligence, the obvious constraints usually come to mind: global NVIDIA GPU shortages and local electrical grid capacity. Beneath these hardware and power limits lies a stricter physical reality. The actual barrier threatening the expansion of the tech industry is severe water scarcity. To process large-scale inference tasks, a single massive AI data center consumes millions of liters of water every single day. Over the course of a year, that daily draw compounds into roughly 1 billion gallons of water evaporated into the atmosphere. This visual scale comparison shows what that billion-gallon footprint actually looks like. A single facility requires the exact same annual water supply as a city of 50,000 people. To build production-ready systems, software engineers must stop treating the cloud as an abstract void. Computation is a physical process with extreme biological costs. The financial reality of this infrastructure crisis became undeniable in the June 2026 IPO prospectus filed by Elon Musk's SpaceX. In that filing, the company amended investor expectations by explicitly detailing a massive new risk factor. SpaceX warned Wall Street that their long-term AI data center expansion is explicitly constrained by water scarcity and the availability of economically feasible cooling resources. Tech companies typically cite competitive pressure or chip availability as primary risks. SpaceX has instead identified the thermodynamic cost of water as a direct cap on its expansion. The geography dictates the limit. Data center expansion halts if the physical territory meant to house those servers faces severe droughts or regulatory water bans. No amount of engineering capital can scale a digital brain if the local environment lacks the basic biological resources to cool it. To understand why deep learning consumes so much water, we have to look at the foundational physics. Processing multi-agent loops across a hyperdense cluster of GPUs requires intense energy. These massive inference tasks pull incredible amounts of electrical current through the processor, and that electricity instantly converts into immense thermal waste. If you fail to dump that thermal heat immediately, the system enters a failure state. The processors experience severe thermal throttling, drastically slowing down computation. Pushed beyond the throttling limit, the extreme heat causes permanent physical damage to the silicon wafers themselves. The cheapest standard for mitigating this thermal threat is evaporative cooling, observed in this 3D isometric server model. In this cycle, water flows over the server plates, absorbing thermal energy directly from the hot processors. The absorbed heat is then transferred outside, where the heated water is quite literally boiled off and vented into the atmosphere through massive cooling towers. Executing this thermodynamic process for thousands of server racks simultaneously requires the type of real-world industrial infrastructure seen here. This establishes the core thermodynamic law of modern artificial intelligence. Compute directly equals heat, and heat directly equals evaporation. Because available physical territory is rapidly running out of water, engineering capital is actively flowing away from these open evaporative systems. In late 2026, tech giants like Microsoft and OpenAI began spearheading an architectural shift toward anhydrous, or completely water-free cooling. This blueprint shows the mechanics of new closed-loop systems. Instead of boiling water, they use giant mechanical radiators to reuse the exact same fluid. This design prevents water loss, relying entirely on heavy-duty airflow and mechanical fans to dissipate heat. But the engineering goes to even further extremes. SpaceX recently revealed drafts for orbiting artificial intelligence satellite data centers. These orbital centers utilize active liquid-ammonia loops to capture internal server temperatures and radiate heat directly into the freezing vacuum of space. Enterprise companies are now willing to design massive mechanical closed loops or launch servers straight into orbit, entirely to escape Earth's strict thermodynamic and water constraints. This physical reality dictates a hard shift in professional software development. Enterprise companies now demand systems engineers who understand the specific hardware footprint generated by their code. A common point of failure in modern technical interviews occurs when an applicant treats all artificial intelligence models as having the exact same computational weight. Multimodal deep learning transformers and shallow neural networks are entirely distinct subjects with drastically different architectural complexities. This flowchart illustrates the cost of a deep learning transformer. Deploying one requires megawatts of compute, draining a distant cloud data center. Contrast that heavy routing with a basic neural network executing a shallow task on a low-power edge device. Those shallow, localized tasks bypass the cloud entirely, running on a local device for an absolute zero water cost. If an engineer cannot distinguish between the footprint of these two domains, they cannot calculate the true environmental and financial cost of their deployment. Modern system design evaluates physical resource consumption with the same rigor once reserved for database optimization. This is why the execution of small language models, or SLMs, is becoming the primary optimization strategy for the upcoming 2026 hackathons. This systems map traces how hyper-optimized code running on a local SLM executes locally with a green check for zero water cost, actively bypassing the red warning of a massive cloud data center call entirely. The physical reality of the localized server hardware running these edge deployments proves that high-scale operations don't always require massive, distant infrastructure. True engineering prowess now means designing applications that inherently respect the strict physical limits of power, space, and water. The infinite ambition of artificial intelligence software has finally collided with the hard thermodynamic limits of the physical world. The software engineers who succeed today are the ones who can write hyper-optimized, resource-aware code. If you want to see a technical breakdown of how to build an application specifically optimized for local edge deployment to eliminate cloud compute overhead, let me know in the comments. Subscribe to stay sharp. Remember, abstract code has undeniable physical consequences. Class dismissed.